Spent a lot of time talking about the sine and cosine functions, graphing those, applying applications to those. But now it's time to talk about the other four trigonometric functions. So today you're going to learn how to graph those, and then pretty much after that we're just going to go ahead and move forward. Okay? Really not too much application stuff that goes along with the other trig functions, but you do need to know how to graph those. So here we go. Looking at that yellow foldable from the very beginning of the chapter, where we spent some time talking about the properties of sine and cosine, we're going to do it also for the remaining four. So we're going to start with cosecant. Now, who remembers what trig function cosecant was the reciprocal of? Sine. It was the reciprocal of sine. Okay? And so when it comes to graphing the cosecant function, one way to do is you can use the graph of sine as a guide for it. Okay? You can use it as a guide. So, cosecant is the reciprocal of sine. So we still have the same big 5, and remember, we're not gonna consider these ones in the middle. So I'm just gonna go ahead and cross this out because it's we are going to include a 0, okay? And so we know that the sign of 0 is what? What's the sign of 0? 0. But since this is cosecant, it's 1 over 0, which is what? Undefined. Okay? Because you can't divide by 0, which basically means that if it's undefined, there's actually a vertical asymptote on this graph. Okay? So cosecant is going to have some vertical asymptotes because this is not the only time where you're going to end up with 1 over 0. What was the sine of pi over 2? 1. What's 1 over 1? 1. Pi. What's the sine of pi? 0. 1 over 0 is? Undefined. And again, we're going to have another asymptote. What was the sine of 3 pi over 2? So 1 over negative 1 is? Negative 1. And last but not least, 2 pi. What was the sign of 2 pi? 0. 1 over 0 is? Undefined. So, you're going to end up having asymptotes here on the graph of cosecant. Now, what I'm going to do is I'm going to take old school sine, which was 0, 1, 0, negative 1, 0, and I'm going to graph it just real quickly on this graph. Ooh, can y'all see that? Can y'all see gray? No. No? Okay. That's a fancy pen. It is. So I'm going to go ahead and put sine in here. Okay? And if I follow that same pattern going in the negative direction, I should go down, right? Then back up to 0. Then up to 1, then back to 0. That is the graph of sine. Now, if you notice on the sine graph, at every x-intercept is undefined on the cosecant graph, right? So, again, that meant that we have asymptotes at every x-intercept on the sine graph. So I'm going to go ahead and add those in. Even on the negative side. Now I'm going to put in these other points. At pi over 2, I'm at 1. 3 pi over 2, I'm at negative 1. Now the graph of cosecant, it looks like so. Now, I know I took out those points that are, in between 0 and pi and in between pi and 2 pi, but they do indeed continue to either increase in that first section and then decrease in that second section. So yeah?
Cosecant, the first one to the right, it's always going to be pointing up.
For your basic parent graph, yes.
So it just depends on whether or not it's on the positive side or the negative side.
Mm-hmm. And the truth of the matter is basically wherever there's a max a maximum on the sine graph, you basically have a parabola that's opening up. Wherever there's a min on the sine graph, you have a parabola that's opening down. So even here, you have a minimum, so that means you're going to have your cosecant graph opening down. At negative 3 pi over 2, you have a maximum, so that graph is going to open up.
Will the direction ever change?
Will the what?
Direction of parabolas ever change?
They will only change if, like, let's say you were to reflect it over your x-axis. But again, wherever there's a max, there's going to be a parabola pointing up. Wherever there's a min, it's going to be pointing down. That's why it's kind of always nice to have like that sine function in there whenever you're doing cosecant, because again, where there's a max, it goes up, min, it goes down. And also, where it crosses that x-axis, where it has normally the zeros, that's where your asymptotes are going to be as well. Okay? Now, let's identify how often these asymptotes are going to occur, because again, this is just between negative 2 pi and 2 pi. It goes on forever. And the asymptotes are going to be at the same spot as you go along in this graph. Okay? So, when it comes to identifying how often the asymptotes occur, take a look at how far apart they are. How far apart are these two asymptotes here? They're pi units. And so basically, since they're pi units apart, and one of your asymptotes is at 0, it's going to continue to occur at every pi. 0, pi, 2 pi. The next one will probably be at
3 pi.
And then
4 pi.
So how do I represent that in the general sense? How would I represent every pi as my asymptotes? I had an issue with this first time. But once you get this one again, I know you're going to get back into it. How would I represent that? I need like a general, like a formula almost.
Oh, it would be x pi plus pi.
Close. I do need a variable. You are right to say x pi. I'm going to change it to n because x's might get confused with zeros. N pi, where n would be a what? To represent every pi and then 2 pi. It would have to be an integer because we have negative pi, don't we? Negative 2 pi. The one before that would be at negative 3 pi. So your asymptotes occur at every n pi, or pi n, and n would have to be an integer. And because your asymptotes occur at every n pi, that is going to affect your domain. Because the domain is everywhere the function is defined. Asymptotes are everywhere the function is not defined. So to represent our domain of our cosecant function, it's going to be the set of x values such that x does not equal n pi. Because if x equals n pi, we're at an asymptote. And it's undefined. Does that make sense? Let's look at the range. What is the range of this graph? Negative infinity to positive infinity?
Because it keeps going up and it keeps going down.
Ah, but is it every y value?
No.
It's not 0. It's actually no values that are in between 1 and negative 1. So it's actually every y value that is greater than or equal to 1 and every y value that's less than or equal to negative 1. So you can either write that in interval notation or you could write it in set notation. So it's everywhere except in between negative 1 and 1. Do y'all remember what the definition of amplitude was? From the midline to the max, or from the midline to the min, correct? Don't have that here. Okay, unlike on your sine graph, which you can still see in orange, the midline would be 0, and that distance between the midline to the max would be 1. There is none. Okay, because as these continue to increase, there's no like midline that's up in the positive infinity area or a midline that's down in the negative infinities. So there are no amplitudes on your cosecant function. What about my zeros? Are there any zeros? What's another word for zeros? Does this graph cross the x-axis?
No.
The blue graph. No, the blue graph doesn't. So we do not have any zeros either. So no amplitude, no zeros. However, we do have some maxes, don't we? Where does one of your maxes occur? The x value. Negative pi over 2. So one occurs at negative pi over 2, but there's multiple relative maximums on this graph. So it's negative pi over 2 plus, how far apart are these maxes from each other? How far is negative pi over 2 from 3 pi over 2? It's 2 pi. Every max is going to occur every 2 pi from one of them. So you represent that as 2n pi. Every relative max is going to occur at every negative pi over 2 plus 2n pi. N, of course, is a what? An integer. So if n were 1, that would be negative pi over 2 plus 2 pi. And if you add that, you do get 3 pi over 2. If you continue to add a 2 pi, you'll get the next one. Add a 2 pi, you get the next one. Add a 2 pi, you get the next one. What about your relative min? Pi over 2. And then the next one's going to occur every, how often?
Same 2 pi.
2 pi, so then we represent that as? 2n pi. Anytime you have to represent multiple asymptotes or multiple maximums or multiple minimums, okay, it's going to be however far apart they are times n. Okay? Your asymptotes. They were pi units apart. You pick one of the one to start with. 0 happened to be one of them, so then 0 plus n pi. You don't have to put the 0, that's why it's only n pi. What's the period? How long is your cycle before it starts to repeat itself?
2 pi.
2 pi. So it's no different from the original sine graph. And those are your features of cosecant.
So there's never going to be a number in front of the cosecant.
There can be a number in front, but that just tells you how stretched the graph is. But it doesn't tell you the amplitude.
Okay.
It just tells you how stretched it is.
Pi over 2, that's like the first, that's like where you start for each.
You can, to be honest, you can, for your relative maxes and mins, when it comes from like what this first starting number is, it just needs to be one of them. So it needs to be wherever one of your maxes is located plus how far apart they are. So I really could have said for relative max, I could have said 3 pi over 2 plus 2n pi. Okay? But it just needs to be one of the starting ones and then plus whatever. Same thing with the asymptotes. I could have said pi plus n pi, but it also turns 0. Let's look at secants. And then we're going to get to some graphing of these. Okay? So let's look at secant. Secant is the reciprocal of which one? Cosine. So that's 1 over cosine. Again, we're only going to look at the big 5. Let's run through cosine real quick. What's the cosine of 0? 1. Cosine of pi over 2?
0.
Keep going. And, awesome, okay? So then when we're doing secant, it's 1 over that value. So what's 1 over 1? 1. What's 1 over 0?
Undefined.
What's 1 over negative 1?
Negative 1.
1 over 0?
Undefined.
1 over 1?
1.
Again, wherever there were zeros on your cosine function, it's undefined, which means you're going to have a what there?
Vertical asymptote.
A vertical asymptote. So in this tan color, I'm going to graph cosine very lightly. So then that way you can see how you can use that to help. So I have an asymptote as pi over 2 and 3 pi over 2. How would I represent every asymptote? Remember, you pick one to start with, so give me one of the asymptotes. Plus how far apart they are. How far apart are those asymptotes? Pi units, so then it's going to be n pi. Of course, n is an integer. N is an integer applies to all the times we use n. So if that's the case, where are my other asymptotes on my negative side? Negative pi over 2 and negative 3 pi over 2. Okay? And every 0 on the cosine function, but also every pi units away from each other. Now, to get the rest of the graph, at 0, I'm at 1. At pi, I'm at negative 1. And at 2 pi, I'm at 1. Secant is very similar to cosine, meaning that if you're at a maximum on your cosine function, that means your graph is going to point up. And if you're at a minimum on your cosine function, the graph is going to point down. Here, I'm at a maximum, so I'm going to point up, and I'm only going to do the half. I don't have the rest of the graph. At negative pi, the graph of secant is going to point down. And then at negative 2 pi, the graph of secant is going to point up. So in the purple, you have your graph of secant x. What's the period of secant? Still 2 pi, very good. To be honest, it's going to be whatever the cosine function would be, okay? They stayed the same. So cosine's 2 pi, secant's 2 pi. If cosine's 4 pi, then secant is 4 pi. Yes?
Would that be the same for sine and cosine?
Yes, exactly. Secant and cosecant. Let's go domain. Is it all real numbers? It's all real numbers, but the so the set of x values such that x does not equal our asymptotes, which were pi over 2 plus n pi. What's my amplitude?
None.
What about my zeros?
None.
Doesn't cross the x-axis, and it doesn't have a restriction to show how high it goes. Let's identify all the relative maximums. You need one of them. Give me one maximum.
Pi.
I could say pi. Now, how far apart are the maximums? 2 pi. So then you're going to put 2 n pi to represent everyone. What about my relative mins? 0. How far apart are they?
2 pi.
So I could just put
2 n pi.
2 n pi. I don't have to put the 0. I mean, you could, but you don't have to. And remember, I could have also used 2 pi and said 2 pi plus 2 n pi. I just need one of them. Last thing, what's my range?
Negative infinity to 1, then 1, and then 1 to infinity.
And the 1 and the negative 1 are included because you have a relative max or relative min in each of those. So it's defined. To graph these, to graph any complex secant or cosecant function, if you can graph the sine and cosine of it, all you have to do is add in your asymptotes and then do your ups and downs. Okay? That's what we're about to do. Okay? So going on the white sheet of paper for your notes, we're going to graph two of these functions, one secant, one cosecant. Okay? So you can see how it works. Let's get that one. We're going to do this one. Okay? We're going to try to do the most complex one possible. Okay? So we're going to do y equals cosecant negative x minus pi plus 2. Y equals cosecant negative x minus pi plus 2. Whatever type of transformations or changes that happen to its reciprocal function are going to happen to this function. And we use the reciprocal function to graph this. What's the reciprocal of cosecant? Sine. So when it comes down to our table, because we're still going to use the table, I'm going to use those respective values. And I still affect the x's and the y's the same way we did before. We're going to multiply all of our x's by what? 1 over b. What's b in this problem? So we're going to multiply all of our x's by 1 over negative 1, which is just negative 1. And then we're going to do what? Plus or minus the phase shift. Now, we're going to figure out the phase shift. The formula is what for phase shift? What's a negative? What's c?
Negative pi.
So that's a negative pi all over. It is the absolute value of b. So it's just going to be 1. So a negative make a?
Positive.
So I'm going to add pi to all my x's. What's happening to my y's? Add 2. Okay? And remember, this is sine. So what y values am I using? Okay. So go ahead and complete my table. Hold off on the graphing part, but go ahead and complete my table. So give myself some more space. What are my x's? Pi. Okay. What are my y's? Okay. So this is what I'm going to use to graph my sine function. Now, if you notice, y'all don't have any space here. And when I did this slide last year, I was like, oh, I messed up. Let me add this in. But, we need to practice being able to continue to graph beyond, just this little bit. So I'm going to graph what I can. I know at pi I'm at 2. At pi over 2 I'm at 3. At 0 I'm at 2. Now if I were to continue the rest of it, it would be going backwards. But look at how these points are spaced out. Look at the pattern. Going up. The next y value would be what after this point, going to the right?
1.
It would be 1. And where would it occur?
At 3 pi over 2.
3 pi over 2. So remember, these are sinusoidal functions. Everything is spaced out equally. So if you have a point at 0, if you have a point at pi over 2, you have a point at pi, these are equally spaced out in integers of pi. Pi over 2. So the next one would be at 3 pi over 2, and it would be at 1. And if you think of what the graph of sine looks like, the next y value should be where? At 2, and it would be located at 2 pi. Okay, so not even looking at this, I'm not using this here. I'm only using that graph that I gave you. So then, very lightly, I'm going to put my dots in to represent the sine function. And now I'm actually going to graph the full thing. Because this is sine negative x minus pi plus 2. I need cosecant, which means I need asymptotes in here, and I need the mini quadratics going up and down. Okay? Now, the asymptotes, they occur wherever there's a 0. Now, we did move this graph up, but the zeros are still the zeros. So I should have an asymptote at here. I should have it at negative pi. I should have it at 0. I should have it at pi, and I should have it at 2 pi. Because that's technically where it would have been had I not shifted the graph up. So I'm going to draw my asymptotes. And remember, wherever there is a maximum on the graph of sine, the little parabola is going to point up or down? Up. And they're asymptotes, so they should get close but never cross or touch. And if there's a minimum,
It points down.
And that is the graph of cosecant negative x minus pi plus 2.
So I had a number in front of it. What would you do? You just treat it like a normal A.
You do treat like, if there was a number of frames, you treat like the normal A, so you would have a vertical stretch, and then these would be further spaced out from each other. Like the maxes and the mins on the black graph would be further spaced out. Let's do a secant one, not that one. Or that one. Let's do this one. So y equals negative secant 2x minus 3. Negative secant 2x minus 3. What's going to happen to my x's? Multiply my y in half. Anything else? Do we have a facia? No. So that's it. What's going to happen to my y's? Subtract 3. Now, this is what we're going to do to the reciprocal function, which is cosine. So we're going to do our table for a normal cosine. We're going to lightly draw in cosine, and then wherever there would have been x-intercepts, we're going to draw in asymptotes. Okay? I have my big 5. All my big 5 is going to get multiplied by 1/2, so that's going to be 0, pi over 4, pi over 2, 3 pi over 4, and pi. And since this is cosine,
It'd be you start at 1
start at 1.
and 0. Negative 1, 0, 1.
So I already know my asymptotes are going to occur at pi over 4 and 3 pi over 4 because that's where my zeros would have been. But this graph is getting flipped and it's getting moved. So when I multiply 1 by negative 1 and subtract 3, what's the value? Negative 3, negative 2, negative 3, negative 4. Let's get those values in. Pi over 4 is halfway in between 0 and pi over 2. What way? But remember, when the period gets changed, everything gets like switched in or pulled out. So that means the asymptotes are going to change as well. Yeah. So that's why we want to make sure we do those transformations, and then that's where the asymptotes are going to occur on those changes. Now, if I keep following the same pattern to get the other points, the next y value should be where? Should be negative 3, and it should be halfway in between, right? Here we go. It technically would be a 5 pi over 4, right? What would be my next one? 3 pi over 2, and I should be at negative 2. Next one after that should be
So something with 4.
something with the 4. 7 power of 4. And what's the y value? And the last one should be at
2 pi negative 4.
So there we go. Cosine's been flipped upside down, and it's been moved down 3 units. I'm going to add in my asymptotes at pi over 4. And 3 pi over 4. Anywhere there's a negative 3, exactly, which were all my over 4s. And then you add the parabolas to the maxes and the mins. I have a min here, so I have a parabola that points down, and only half of one. I have a max here, so I should have a parabola that points. I have a min here, max, min, there's only half of one. And there you have your graph of negative secant 2x minus 3. So when it comes to, continuing the graph, like to fill the entire graph that I'm giving you, yes, recognize the pattern. There being the space between each of the points is a pi over 4. So the next one would have been 5 pi over 4, then 3 pi over 2, then 7 pi over 4, so on and so forth. Okay? Try to figure out that spacing, yes.
So would the period here be pi?
So the period here would be pi, yes. And if you look between one complete cycle, that's 1 up and 1 down, that was between pi over 4 and 3 pi over 4 for a total of pi. If I asked you to write down where the asymptotes are for this particular graph, remember, when you change the period, those asymptotes are going to change from the original. So you start with one of your asymptotes. Where do one of your asymptotes occur? Pi over 4. And then you add how far apart they are. How far apart are my asymptotes from each other? Pi. So then you do a plus n pi. That's how you identify your asymptotes. Start with one of your asymptotes. You could have said 3 pi over 4. It didn't matter. But it did matter how far apart they are. Let's do the same thing with the one that we did before. I want you to identify my asymptotes. You locate one of your asymptotes. Where do one of your asymptotes occur? At 0. How far apart are they? So I'm going to add, and I really could have just said n pi, but I just want to make sure to harp on that. What was the period for this one?
2 pi.
2 pi. Remember, the formula is still 2 pi over the absolute value of v, so that's still the same.